Hello everyone, this is the fourth lecture of week 4. Please recall that in the previous lectures we learnt about the gradient descent algorithm and the drawback. So, when the function to be minimized is a quadratic function and the Hessian of the quadratic function has its eigenvalues, the ratio of the highest the lowest eigenvalue to its highest eigenvalue is much less than 1. Okay. So, we saw that the number of iterations is huge in gradient descent algorithm. So, we were trying to rectify them and so we first attempted coordinate descent algorithm and then we did a change of coordinates. And what are the coordinates? Change of axis, so as to say. The axis is based on the eigenvectors of the Hessian matrix, right. So, we did that until the previous lecture. So, there are two issues with this eigenvector method that we discussed in the previous lecture. The first one is finding the eigenvector is computationally expensive, okay, finding all the eigenvectors in fact, right. So, that is computationally expensive. So, we want to check if there is a better method, right. So, where it is not computationally expensive. And the second, we also want to extend this to functions which are not quadratic. So, how should we do that? So, that is another thing that we should consider as well. So, we will discuss about that in this lecture and the next lecture. So, you can recall that when we had this particular function to minimize, right. So, h was 2 1 1 2 and we chose a scalar multiple of 1 comma 1 and 1 comma minus 1 as the directions, right. So, before going to more sophisticated questions, we should first ask this question: can we actually attain the solution by any other set of directions? So, let us take h is equal to 2 1 1 2 itself, okay, and suppose I take some other d 0 and some other d 1. So, can I still attain the minimum in 2 steps? So, let us first ask that question, okay. So, I am going to make an attempt at this point, okay. So, let us again consider f of x 1 x 2 equal to half x transpose 2 1 1 2 x, and let us say x 0 is 4 comma minus 5 as we had in the previous illustration as well, and let us put d 0 equal to 1 comma 0, okay. Of course, d 0 equal to 1 comma 0 and 0 comma 1 is not going to work, but I will figure out what d 1 is in a little while, okay. First, but let us start with 1 comma 0 at this point, okay. So, we will have x 1 equals x 0 plus alpha 0 d 0, right. So, x 0 is 4 comma minus 5 and so we will figure out what g 0 and g 0 transpose d 0 everything is. So, g 0 is h x naught basically. So, it is 2 1 1 2 4 minus 5 which is 3 and 4 minus 10 is minus 6. So, g 0 transpose d 0 is 3 and d 0 transpose h d 0 is 2, right. So, we write 3 by 2 1 0, which is just 2.5 minus 5. The first element is 4 minus 1.5, which is 2.5, and the second element remains the same, which is minus 5. Okay. All right. So, now I am going to choose D1 as D1 as 1 comma minus 2. Okay. So, yeah, we will explain this choice in a little while, but let us proceed with this. So, we will have x 2 equals x 1 plus alpha 1 d 1. So, that is 2.5 minus 5, and let us compute what is g 1, that is 2 1 1 2 2.5 minus 5. So, you have 5 minus 5, which is 0, and 2.5, am I doing it right? Yes. So, yeah, 2.5 minus 10 is minus 7.5, okay, and G 1 transpose D 1 is, so yeah, this is 15, and D 0 transpose H D 0 is, so you will have 5 minus 4 is 1 and plus 8 is 9. So, we have minus 15 by 9, 1 minus 2. So, yeah, 15 by 9 is 5 by 3. Okay, so, let me see what is D 0 transpose H D 0 again. So, it is 2 plus 8 10, 10 minus 4 6, I am sorry, yeah. Yeah, now that clarifies, yes, it is 15 by 6. So, yeah, so now you have 2.5 minus 15 by 6 is 2.5. So, 2.5 minus 2.5 is 0, and minus 5 minus 5 is 0 again. Okay. So, you can see that I used D 0 equal to 1 comma 0 and D 1 equal to 1 comma minus 2, okay, which is very different from what we had here, right. So, we had minus 1 and 1 minus 1, right. So, if you compare that, what we had here, D 0 is 1 0 and D 1 is 1 minus 2. So, with a very different set of directions, again I was able to get to the answer. So, what this tells us, at least at this point, is that eigenvectors are not the unique set of directions that we can consider and still manage to get the final answer. Okay. So, fine, if those are not the only set, how do you construct this 1 0 and 1 minus 2? So, that is possibly a more important question. So, what I claim is the following. So, consider minimizing a quadratic function with its Hessian being positive definite, H being positive definite, then the algorithm converges to the solution in at most n steps if we choose d 0, d 1 dot 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 d n minus 1 such that di transpose H d j equal to 0 for all I not equal to j. Okay. Yeah, of course, it has to be used with exact line search, okay, and exact line search is used. Is used at each iteration to compute the step size. Okay. So, what I claim is find out the directions d0, d1 dot 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 dn minus 1 such that this condition is satisfied, dA transpose H dj equal to 0. Okay. So, of course, when I not equal to j, and if you succeed in finding them, I claim that the quadratic function can be minimized in n iterations. Okay. So, the first question you should have after reading this claim is, does the eigenvectors satisfy these conditions, right. So, let us verify that quickly. Okay. So, let us say that, so if di dj are such that h di is lambda I di and h dj is lambda j dj. Okay. So, then you can see that dI transpose H dj is lambda I di lambda j dI transpose dj, but dI transpose dj is 0, right. So, the eigenvectors of any symmetric matrix are orthogonal, right. So, since dI transpose dj is equal to 0, so you can see that dI transpose H dj equal to 0 whenever I not equal to j. Okay. So, that is very clear, and that is the reason why I mean when you used eigenvectors, we reached the answer in n steps. Okay. So, you can see that here as well, right. So, you have d0 is 1 0 and d1 is 1 minus 2. So, if you check what is d0 transpose H d1, right. So, H d1 is 2 1 1 2 into 1 minus 2, right. So, that is 2 minus 2, that is 0, this is 1 0 and so this is 0 and 1 minus 4 is minus 3. So, yeah, you can see that this is 0, right. So, that is the reason why I actually got in 2 steps I actually converged to the solution, right. So, so we have I mean we have given some examples as to say why choosing dI transpose H dj equal to 0 for all I not equal to j and using exact line search actually gives you the answer, right. So, now the question is, how do you find such directions, right. So, suppose I give you an arbitrary symmetric positive definite matrix, right, with so yeah, I give you a quadratic function and H is really arbitrary, right. So, how do you come up with d0 d1 dot 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 dn minus 1? Of course, you can use eigenvectors. I have said it is computationally inefficient, right. So, it is not just that you should come up with some d0 to dn minus 1, but you should also come up with a computational method which is efficient, okay, at least faster than computing the eigenvectors, right. So, that is the challenge. Okay. So, I will now discuss a method of coming up with d0 d1 dot dot dn minus 1, and this method was actually given by two people called Fletcher and Reeves. Okay. So, I mean we will call these as call this as the Fletcher-Reeves algorithm. Okay. And before that, so when you have these kind of vectors where you have di transpose H dj equal to 0, right. So, these vectors are actually called as H conjugate vectors. Okay. So, vectors d0 to dn minus 1 that satisfy di transpose H dj equal to 0 are called H conjugate vectors. Okay. So, this is a name that we will repeatedly use. So, I wanted to let you know about this. Okay. And the other one that I wanted to say was I mean the algorithm that uses H conjugate vectors as the directions of as the descent directions in each iteration is called a conjugate gradient algorithm. Okay. So, this is a name that I mean you might have heard from the topic of this week, and the I mean so even during the lectures I might have told you this name of the algorithm, that conjugate gradient algorithm, right. So, using eigenvectors of H is one form of conjugate gradient algorithm, right, where you actually choose H conjugate vectors, but there is a specific form of H conjugate vectors that you actually use, right. So, that is a form of conjugate gradient algorithm. I am going at this point I am actually going to give you the Fletcher-Reeves form of conjugate gradient algorithm. Okay. So, let me go ahead with that. So, what I am going to do is I am going to fix okay. So, fix d0 as minus g0, that is it is same like the gradient descent algorithm, negative of the gradient of f at x0. So, for d1 I am going to fix minus g1 plus beta naught d naught, okay, and d2 is minus g2 plus beta naught d1 plus beta naught d naught plus beta 1 d1, okay, and so on until dn equals or dn minus 1 equals minus gn minus 1 plus beta naught d naught plus dot 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 beta n minus 1 dn minus 2. Okay. In general, dj is minus gj plus summation beta I di I equal to 0 to j minus 1. Okay. So, for all j from 0 to n minus 1. Okay. So, we will have to figure out what beta I is. Okay. So, we will figure that out in such a way that these dj's actually satisfy di transpose H dj equal to 0. Okay. So, now let us say we put di transpose H dj. So, what I am doing is I am pre multiplying by di transpose H in I mean throughout this equation, right. So, I will have minus d I transpose H g j plus summation beta j okay. Maybe I will use a slightly different notation, maybe d L transpose, so that it does not confuse with the running index. So, yeah, here you have d L transpose H d I equal to 0 to j minus 1, right. So, note that we want the left hand side to be 0 for any L not equal to j, right. So, what happens is this is 0 and this is minus d L transpose H d g j, and this is 0 if L is sorry I is not L, right. So, you will have this as beta L d L transpose H d L, right. So, therefore, beta L is d L transpose H g j by d L transpose H d L. Okay. So, or yeah, in the numerator I can take a transpose, nothing is lost by that. So, I will write as g j transpose H d L. Okay. Yeah, so that is the value of beta L, right. So, therefore, from what you have here, you have d j equal to minus g j plus summation beta I d I, right. So, you have d j equals minus g j plus summation I equal to 0 to j minus 1. So, g j transpose H d I by d I transpose H d I d I. Okay. So, you can see that d j is minus g j, which is what we would have chosen if we had used the steepest descent algorithm or the gradient descent algorithm, right. So, but in this form, the Fletcher-Reeves form of conjugate gradient algorithm, we write minus g j plus summation some scalar into d I, that is with minus g j you add certain scalar multiples of d I as well. Okay. So, when I do this, you can see that this condition of d I transpose H d j equal to 0 is satisfied, because that is how I have figured out beta i's. Okay. So, but one thing is this can actually be simplified. So, yeah, this again seems to be I mean not an easy formula to calculate, right. So, we can simplify this. How do we do that? So, yeah, note that we know x I plus 1 is x I plus alpha I d I, right. So, that means h x I plus 1 plus b equals h x I plus b plus alpha I h d I, right. So, this is nothing but g I plus 1 and this is g I, and yeah, here you have alpha I h d I. So, what this tells us is h d I is 1 by alpha I into g I plus 1 minus g I, right. So, why is this important? I am going to substitute this here instead of h d I. So, what I have here is d j equal to minus g j plus summation I equal to 0 to j minus 1 g j transpose into gi plus 1 minus gi by di transpose into gi plus 1 minus gi di. Okay. So, I have just substituted instead of h di I substituted 1 by alpha I and this, and since 1 by alpha I is a scalar, they cancel in both the numerator and the denominator. So, I had Gj transpose into Gi plus 1 minus Gi. Okay. So, that is basically what we have here. Okay. And I can simplify this further, and how is that? So, please note that okay, so I need to actually show something. So, this is an aside, I mean I will use that here in a short while. So, yeah, so again we will start with this. So, xk is xi plus summation, okay, maybe I will write as xj, summation alpha I di, where this goes, so I goes from j plus 1 to k minus 1, right. So, now it goes from j to k minus 1. So, I have just written, so for x0 we write x1 we write x0 plus alpha 0 d0, for x2 I can write it as x0 plus alpha 0 d0 plus alpha 1 d1, right. So, I mean that is what I have written it in a sophisticated form. Okay. So, now I will multiply h and add c like what I did here. Okay. So, we have hxk plus c equals hxj plus sorry hxk plus b equals hxj plus b plus summation I equal to j minus 1 alpha I h di. Okay. Now, suppose yeah, so this is just gk equals gj plus summation I equal to j to k minus 1 alpha I h di. Okay. So, yeah, so now I will yeah multiply dl transpose throughout. Okay. So, we will have gk transpose dl equal to gj transpose dl plus summation I equal to j to k minus 1 alpha I dl transpose h di, right. So, yeah, we have gk transpose dl equals gj transpose dl plus summation I equal to j to k minus 1 alpha I dl transpose h di. Okay. So, yeah, suppose I let L equal to j. Okay. So, I will solve for that case. Okay. So, in that case we have gk transpose dj equals gj transpose dj plus, so except j all the other dl transpose h di is equal to 0. So, you have alpha j into dj transpose h dj. Okay. But recall what is alpha j? Alpha j is minus gj transpose by dj transpose h dj. So, if I substitute that, I will have gj transpose dj minus yeah, so it is just gj transpose dj by dj transpose h dj into dj transpose h dj, which is 0. Okay. So, note that gk transpose dj is equal to 0 for any j, right. So, the j here was arbitrary, I can choose I mean of course, j should be less than k, j can be 0, j can be 1 dot 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 j can be k minus 1. So, for any j such that k is greater than j, okay, where j is greater than k. Okay. So, we can write that, so
therefore, gk transpose dj equal to 0 for all j equal to 0 1 dot j minus 1. So, this is something that needs to be understood. So, the proof of that fact is given here. Okay. So, this is the proof for the fact that gk transpose dj is equal to 0. Okay. And the other thing that you have to note is from here. Okay. So, note that d0 is minus g0 and so on, right. So, that means I can write. So, the other way of writing this is g0 equal to minus d0, right, and g1 equals b naught d naught minus d1, g2 equals b naught d naught plus beta 1 d beta naught d naught plus beta 1 d1 minus d2 and so on, right. So, what happens to gk transpose gk transpose gj? So, that will just be gk transpose into beta naught d naught plus beta 1 d1 plus dot plus beta j minus 1 dj minus dj minus 1 and minus dj, right. So, note that gk transpose d0 is 0, gk transpose d1 is 0 and so on. So, this is 0 for all j in 0 to this is k minus 1. Okay. So, the basic point that I want to stress is that gk transpose gj equal to 0 when k is greater than j. Okay. So, apply that here. Okay. So, you can see that if I is not j minus 1, right. So, the numerator becomes 0 for everything else, and when I equal to j minus 1, this term becomes 0 as well. So, you just have dj equal to minus gj plus summation gj transpose gj by dj transpose no summation, because there is only one term when I equal to j minus 1. So, let us just follow that. So, we will have gj transpose gj by dj transpose into gj minus 1 into dj minus 1. Okay. So, this is much more simplified, because here the directions depended on direction at j, jth iteration depended on the directions at all the previous iterations, right. But here you can see that the direction at iteration j depends only on the direction at the iteration j minus 1, right. So, let me tell you, this can be further simplified too. Okay. So, how is that? So, note that dj transpose gj minus 1 is actually 0, right. Sorry, this should be dj minus 1, that is my bad again. Okay. So, this is dj minus 1 transpose, right. So, sorry, dj minus 1 transpose gj is 0 from this. Okay. So, we have dj minus 1 transpose gj equal to 0. So, that is already there. Now, we will also simplify dj minus 1 transpose gj minus 1. We will do that as follows. So, dj minus 1 is actually minus gj minus 1 plus, I am just repeating whatever we had here. So, that is actually bj minus 2 dj minus 2. So, multiplying throughout by minus gj minus 1. So, we have dj minus dj minus 1 transpose gj minus 1 is Gj minus 1 transpose Gj minus 1 plus beta j minus 2 Gj minus 1 transpose Dj minus 2, and this is 0 as well, right, by the same formula. So, we have Gj minus 1 transpose Dj minus 1, therefore, Dj is minus Gj plus Gj transpose Gj by Gj minus 1 transpose Gj minus 1 Dj minus 1. So, yeah, this is how you find the set of directions in Fletcher-Reeves algorithm. We will continue in the next lecture. Thank you.